All right. This is important for you to understand the differences between the actual and the ideal cycle. So certainly we are making some assumptions here. We are making the ideal cycle pretty simple to help with our analysis. So the efficiency and the other things, the work output that we're going to calculate for an ideal cycle will not match with the value that we get from the actual cycle, of course. But the main advantage of doing this simple analysis is to identify what are the different ways in which we can increase the efficiency, right? In an actual cycle, the analysis would be very complicated. You would need to do very detailed computer simulations to identify what's happening. And before we go to a very complicated analysis, it makes sense to identify what's happening in a simple way after making some assumptions to identify what are the main things that you should play with, right? What are the things that affect? So we will see that in the next 20 minutes. So again, to make sure you remember this, Otto cycle has 4 internally reversible processes. Okay, so the first one is isentropic compression from 1 to 2, and it's followed by a heat addition process which happens at constant volume. This constant volume heat addition is the defining factor of the Otto cycle. The heat is added in a constant pressure process when we go to diesel cycle, right? So constant volume heat addition happens only in an Otto cycle. And once you have reached state 3, then we have an isentropic expansion process from 3 to 4. And lastly, from 4 to 1, we have again a constant volume heat rejection. Okay. Now the reason I'm showing this again is because the PV and the TS diagrams are important for these cycles, and you may be asked to draw them. Okay, you may need them to solve a problem as well. So make sure you know how to draw these and you are very clear about what's happening in each of these processes. So as we mentioned before, it's important to talk about the compression ratio. So we said compression ratio was simply a ratio of Vmax by Vmin, right? And the maximum volume here is at V1 at state 1. The minimum volume is at state 2 or V2. Okay, and since 2 to 3 and 4 to 1 are constant volume processes, it's also equal to V4 by V3. All right, so this is the compression ratio for an Otto cycle. Okay, so now let's talk about the energy balances for the Otto cycle. As I mentioned before, we are treating this as a closed system. We're treating reciprocating engines as a closed system because air is not going out nor fresh air is entering in, right? We just are making use of the same air. We're just heating it, expanding it, rejecting heat and then compressing it again to move it over a cycle. If we were using a fuel air mixture, that's when we would need to, take fresh fuel, take fresh air in, and then send the exhaust gases out. But here we're not taking a fuel air mixture. We're just taking air. So air can operate in a closed system. Okay, so since we're operating with a closed system, the only modes of energy transfer are heat and work, and the energy change is going to show up as change in the internal energy of the system, delta U. Okay, so if we write the energy balance for each of these processes, well, from 1 to 2, you have the compression process, so it's U2 minus U1. From 2 to 3, we have a constant volume heat addition process, so it's U3 minus U2. And then 3 to 4 is again an isentropic expansion process, U3 minus U4, and 4 to 1 is a constant volume heat rejection process, so it's again U4 minus U1. For each of these processes, we are writing this work and heat transfer simply from the energy balance for that process, right? If you have any questions about how that's happening, we can talk about it during my office hour, or we can set up an appointment. But make sure you understand how to write these different terms, right? It's pretty straightforward. It's just reflecting what's happening during each process. Now, this form right here of the energy balance is basically what you can consider as the general form of energy balance, because it's written for variable specific heats, right? Which is what happens in reality. So that's why we write in terms of internal energies, and the internal energies here, U3, U2, U1, all these are values that you pick up from the ideal gas tables. Okay, now we can make one more assumption, that is we can consider the specific heats to be constant, and when we do that, we can replace the delta U's with CV delta T's. Okay, so we have done that here for Qn and Qout. Now, having defined the energy balances for each of those four processes, it's time that we go ahead and calculate the thermal efficiency. Okay, just like we have been doing for every heat engine that we talk about. So for an Otto cycle, the thermal efficiency as usual is going to be net work output by heat input, or 1 minus Q out by Qn. Now Q out by Qn can be written by using the energy balances that we have described here. So it's U4 minus U1 by U3 minus U2. Now, we would want to make the cold air standard assumptions just to come up with a very simple expression for efficiency. And when we do this assumption, that is when we treat air to be an ideal gas with constant specific heats, we can sort of replace the delta U with CV delta T. Okay, so let me just write what this would be here, what this term would be here when we do such a thing. So this can be written as 1 minus CV times T4 minus T1 divided by CV times T3 minus T2. All right, so we're just replacing delta U's with CV delta T's. Now CV can get cancelled out, and the efficiency formula then comes out to be 1 minus T4 minus T1, like the one that we have here, divided by T3 minus T2. Okay, now here I'm going to take T1 out common in the top and make it in the ratio of T4 by T1 minus 1. And at the bottom, I'm going to take T2 out common, and then the rest becomes T3 by T2 minus 1. There's a very specific reason why I'm doing that, and it'll become clear in a bit. But this mathematical manipulation is something that you don't have to remember, right? But the formula is something that the final formula, the simplified version, is something that it's good to remember. Okay, so we have this sort of a format here. Now let's look at what we can write in terms of T1 by T2. Okay, so 1 to 2 is an isentropic process. So if you're having an ideal gas with constant specific heats undergoing an isentropic process, we have formulas relating the temperature ratios to the specific volume ratios, and also temperature ratios to the pressure ratios. For now, making use of the relation between temperature ratios and specific volume ratios, we can write T1 by T2 as V2 by V1 raised to K minus 1. K is simply the specific heat ratio, Cp by Cv. Okay. Now, since 2 to 3 and 4 to 1 are constant volume processes, V2 is equal to V3 and V4 is equal to V1. Okay, so I can replace V2 by V1 as V3 by V4 raised to K minus 1. And once we have written it in terms of V3 by V4 raised to K minus 1, now using the same relations, I can write this specific heat, specific volume ratios in terms of the temperature ratios. So it comes out to be T4 by T3. Okay. Now what we're essentially saying is T1 by T2 is equal to T4 by T3. Okay. So I can just send T1 down here and T3 at the top, and what I get is T4 by T1. The ratio of T4 by T1 is equal to the ratio of T3 by T2. Okay. So this is all what I have achieved. And why did I bother to do this? Well, because if T4 by T1 is equal to T3 by T2, then these two terms get cancelled out. Okay, those are exactly the same expressions. And the efficiency formula becomes very simple under the cold air standard assumptions. It's simply 1 minus T1 by T2. The temperature at the beginning of the compression process divided by the temperature at the end of the compression process. It's simply a ratio of these two temperatures. So if you know these two temperatures, you can find out the thermal efficiency of an Otto cycle, provided you considering cold air standard assumptions. So this is the beauty of it. This is why we bother making a this is why we bother doing an analysis of an ideal cycle. Okay, and in some ways it sort of resembles the Carnot efficiency formula. Now T1 and T2 are not always known. I mean, you can always calculate them, but these are not values which are given by engine manufacturers, right? On the other hand, what engine manufacturers like to mention is the compression ratio R, right, which is simply V1 by V2. So by using this relation between T1 by T2 and V2 by V1, we can rephrase this. We can write it. We can write this temperature or ratio or the formula for efficiency in terms of the compression ratio in the following way. We can write it as 1 minus R raised to K minus 1. Okay, so T1 by T2 is simply 1 by R raised to K minus 1, and this is what we are writing here. Okay, so R is the compression ratio compression ratio, and it's equal to V1 by V2, and K is the specific heat ratio, Cp by Cv. The value of K is given in table A20. You can pick it up directly from there at the temperature that's mentioned. So what we see from here is the fact that the thermal efficiency of the Otto cycle, it depends on both compression ratio and the specific heat ratio. It's going to increase with both of them. How it's going to increase? Is it going to be a linear increase, non-linear increase? We'll see that in the next slide. Any questions till here?
Clear, Jackson.
Okay. So before we go ahead and look at how the thermal efficiency is increasing with increase in the compression ratio, let's have a look at this TS diagram here to see what's exactly happening. Let's consider the simple version of the Otto cycle, right? Efficiency 1 minus T1 by T2. OK, so let's say this is the T2 and this is T1, and you have a certain efficiency. Now, if you increase the compression ratio, that is for the same value of V1, if you reduce the value of V2, compress the gas a little bit more, what's going to happen is at the end of the compression process, you're going to see a higher temperature. OK, so instead of stopping at T2, you're going to stop at T2 dash. So what we did is we kept T1 constant, but we effectively reduced the temperature. We increased the temperature at the end of the compression process, right? So it's T2 dash now. And when you do that, it's pretty obvious that the efficiency is going to increase, right? Simply because we're also able to achieve a more work output. So this is the simple way in which the efficiency increases with increase in the compression ratio, right? It increases as you keep on increasing the compression ratio. So if you plot the efficiency versus compression ratio, this is how it's going to look like. Initially, any increase in compression ratio is going to increase the efficiency by a huge margin. It's a very steep slope. And then as you keep on increasing, the slope tends to slow down, but it's still always increasing, right? It keeps on increasing throughout. Now, this is what happens with increase. This is what happens on the thermal efficiency with increase in compression ratio, right? You increase compression ratio, thermal efficiency will keep on increasing. Same way, for a given compression ratio, the thermal efficiency will keep on increasing if we increase the value of K, okay, the value of specific heat ratio. Now, specific heat ratio is something which is a function of the working fluid, right? It depends on the molecule that you're dealing with. So for, let's say for air, the value of K is 1.4 at about 300 Kelvin. For noble gases such as argon or helium, the value of K is 1.667. OK, so this is different for different gases. You really can't play much around with it. OK, but it's certainly higher for noble gases. Now, if you want to increase the efficiency of a given heat engine or that's operating on an Otto cycle, there are two ways to it. You can either increase the compression ratio or you could increase K. Now, we can't really have any other working fluid apart from air when we are dealing with the engines in our cars, because air is something that's available around us. We don't have to carry around a tank of air. But if you want to build a stationary power generation system or a system that's that's not moving, that's for generating power in your home or something like that, a backup power generation system, you could make use of other working fluids such as argon and have a simple argon tank and operate it in a closed system, just like the one that we discussed now. And this is going to increase the efficiency by quite a bit, as you can see by looking at here, right? This is a huge jump in efficiency that you have. And this is what a lot of startups are actually doing now for generating power more efficiently, right? So this is, again, when you use some sort of, this is what you can do when you're having a stationary application, meaning you're not moving around, you're just generating power for home or for some specific application, and you can afford to have a huge tank for argon around with you, right? So this is a smart way of doing it. Now, as far as cars are concerned, well, we can't carry around a tank of argon. We would want to use air, which is already available. So the only option there is to increase the compression ratio. OK, and the higher the compression ratio, the higher is the efficiency. All right, and that's always good. But as with everything in life, there is a limit to how high the compression ratio can go. OK, and that is sort of limited by the fuel that we use. So as we keep on increasing the compression ratio, we know that pressure is absolutely going to increase, but the temperature also increases. And at very high compression ratios, you will reach a stage where the pressure and temperature are so high that the fuel air mixture that we are compressing ignites by itself. Okay, so it's what's called the auto ignition, and this is a very undesired phenomenon because it will damage the engine. When we are talking about a gasoline engine or a spark ignition engine, we want the fuel air mixture to ignite only when we send in a spark, because that's the controlled ignition that happens there, right? We want the fuel air mixture should absolutely not ignite by itself. That's not what we want. All right, because when that happens, it's gonna happen somewhere in the middle of the compression stroke, and it'll just create a knocking sound. That's what it's called, engine knock as well. But it also damages the engine, right? Depending on how bad the knock is, it can either break down the engine completely, or it may damage it quite a bit that you may get away with minor repairs. So the compression ratio that we achieve is sort of depending on the fuel that we use, and effectively it depends on how reactive the fuel is, right? If you're having a very relatively more reactive fuel, such as octane 91 that we purchase at the tanks, well, we can't go to very high compression ratios. But if you're having an engine which operates at very high compression ratios, then you may be forced to use octane 95, which is slightly less reactive fuel. Okay, so it allows operating at much higher compression ratios simply because it's not gonna ignite by itself at those compression ratios. Okay, so now this is what we see qualitatively. Increase in compression ratio increases the efficiency, but in reality, there's a range that is typically used depending on the kind of engine you have, right? So the typical compression ratio range is between 9 to 11.5. 11.5 for the engines, the kind of engines that you can find in probably sports cars, or the engines which require high quality fuels. Even 9.6 is sort of the kind of compression ratio that you find in cars like Ferrari and so on. Okay, so this is, yes, go ahead.
We can replace the fuel by methanol, and we can do that. We increase the efficiency.
If you use methanol as a fuel?
Yes.
How do you increase the efficiency? Because you're saying the compression ratio can go high?
Yes.
That's right. So methanol has an advantage that it's not very reactive. So yes, you can go to higher compression ratios. But the problem with methanol is that its energy content is very low. So if you want to, if you have a 50-liter tank of 50-liter fuel tank in your car, you can probably travel 500 kilometers with gasoline that we purchase from the tanks. If you fill in methanol for 50 liters, you will probably be able to travel only 250 to 300 kilometers, not so much. I mean, this is one sort of disadvantage, apart from the fact that it also damages some of the components within your present engine. So you have to modify the engine and the fuel piping a bit. There are disadvantages, but yes, methanol is becoming very popular in China because they can create methanol from a lot of waste resources. And yes, it makes sense. In fact, it's more easier to blend ethanol with fuel, with gasoline, for example. And there are already cars which use, I think, 10% ethanol and so on. So these are called flex fuel cars, and we already have them in the Saudi market as well. So let me just complete this part right here, and then we can have more discussion on that. So the thermal efficiencies that we have in actual spark ignition engines are somewhere in the 25 to 30% range, which are much lower than the values that we see here. And it's simply because we have many more losses that we are not considering in the ideal cycle. But irrespective of that fact, the main utility of the ideal cycle is to show us what are the different ways in which we can increase efficiency, right? And increase in compression ratio is going to increase the efficiency of both actual cycle as actual engine as well as the engine which is operating on an ideal cycle. Same way, increase in the specific heat ratio is going to increase the efficiency in both of them. So basically, we get some ideas on the things that we can play around with. The trends are going to remain the same. All right, I'll stop here. If you have any questions, please stay back and I'll answer all your questions. If you don't have, well, that's the end of the class. We can leave and we'll meet again on Thursday. Before we leave, I just want to tell you that in the next class, we're going to have a pop quiz. Okay, and since the chapter 8 has ended, we will have a quiz on chapter 8 sometime next week. I will send you the details later. This time the quiz for chapter 8 is going to be only multiple choice conceptual questions, so no numericals. All right, so see you in the next class on Thursday, and remember there's going to be a pop quiz, so make sure to attend it.